Okay, yeah, okay. Let me just pull up the PowerPoint for the previous lecture just so I have it for reference. But yeah, let me know if you have any ideas on how to uh, continue this problem. Okay, so the first thing we could do is use a theorem where it says you can just take the absolute value of a sequence instead of looking at the original sequence. So why don't we do that first? If I was to consider the absolute value of the sequence, then that would be equal to just 1 over 2 times the square root of n, right? So the question is this sequence easier to reach a conclusion as to whether it converges or diverges? Yeah. Okay. What do you think we can do? Take the limit. Yeah. So if you were to take the limit as n approaches infinity of 1 over 2 square root of n, what does that give you? Yeah, so the denominator gets bigger, which means the limit goes to 0. So if the limit of the absolute value goes to 0, then the limit of the original series would also go to 0. Okay? So that's how you reach the conclusion. So let me just paste the theorem that we used for this question that was in the previous lecture, previous PowerPoint. So we used this theorem here for this problem. Okay. All right, so that's that one. Any more? Any other questions? Okay, let's see this one. All right, so this is the one you just sent me. Okay, what number is this, by the way? 10. Question 10. All right. Yeah, for this one, I don't think it's too bad. You just plug in infinity, which will, let me write it. So as n goes to infinity, then you just have tan of, uh, you just take the coefficients of the term with the highest power. So it'll just be tan of 4 pi over 16. So this is tan of pi over 4. Yeah, whatever that is. That's your answer. All right, so are we all good? All right, then let's start the next topic. Okay, here it is. So today we're doing 8.2, which is series. So what is a series? We'll start with definition. So we have one definition in this topic, series. So series is a sum of a set of numbers. Yep, that's our only definition. So a sequence is an ordered set of numbers, and then if you just add all of it together, that's a series. Okay, so how do we denote a series? So it's similar to a sequence. It's just instead of having commas in between all the numbers, you have to add them together. So here we have numbers such as a of 1 or a sub 1, a sub 2, a sub 3. And then if you add it all together, you get a sum. So we call that sum like s of 1, s of 2, s of 3, s of 4. And you can see that on the left here in this box. So those sums, s of 1, s of 2, s of 3, s of 4, so those have a special name. It's called a partial sum. The reason why it's called that is because you're adding all the numbers that make up a part of the series. So in this section, we're mostly going to be dealing with infinite series, which means you're adding up infinite numbers. But if you just add like the first 4 numbers, that's s of 4, right? So that would be like a partial sum of the first 4 numbers. So it's called a partial sum. And then other notations include summation notation, which you guys have all seen before. So that's on the bottom right here. Okay, so on the right side of the equal sign, you see summation as I starts from 1. That's your index. And then a sub I is, the current number you're looking at. So it's a sum of a bunch of numbers. If you're looking at an infinite series, then the top index will be infinity because it never ends, okay? All right, so that's how you denote a series. So main idea is that a series is just adding together a bunch of numbers. So there's this thing called the index shift. Typically, we said before that an index starts from 1, but it doesn't have to. So sometimes an index can start from either 3 or 5 or maybe 10 or maybe 0. And there's this process we can do to actually change the index of a series. So let me just read what this says. Sometimes a series is given with an inconvenient starting index. We can perform what's called an index shift to rewrite the series to start at a different index. So here we have an example. the left side of the equation has a series where the index starts at n equals 2, right? So let's say you don't like that. You say, well, I don't want it to start at n equals 2. I want to start at, say, n equals 0. You can rewrite it to start at n equals 0. But if you were to do that, then you would have to go to your formula and you would have to basically shift all your n values up by 2. So the reasoning is follows. You went from an index of 2 to an index of 0. So your index went down by 2. So in your formula, your n values have to go up by 2. So let me write out some middle steps just so you can see how this works. All right. So we are starting with this original series, n equals 2 to infinity of n plus 5 over 2 to the n. So we want to change it so that we start from n equals 0 instead. So how will this change the formula? So to go from n equals 2 to n equals 0, we do minus 2, right? So we had to subtract 2 to go from 2 to 0. That means in your formula, you're going to go to where we see an n, you're going to replace it with a plus 2 instead. So you're going to have n plus 2 plus 5. And then you have a 2 to the power of n plus 2. And then this becomes summation of n equals 0 to infinity of n plus 7 to the power of 2, 2 to the power of n plus 2. Okay, so that's how you perform an index shift. Likewise, if you were to perhaps make the index start at a higher number, then you would subtract a constant from n in the formula. Okay, so that's index shift. Have you guys done this before? No. Okay, so yeah, this is something new then. And then let's take a moment just to convince ourselves that after we perform an index shift, we didn't really change anything about the series. So if you were to write out the numbers in the series for the first one, this would be, actually they have it over here. So look over here, this is the numbers written out for the first series. So it's 7 over 2 squared plus 8 over 2 to the third plus 9 over 2 to the fourth. And then when you do the index shift, which is this one, we shift it to start at n equals 0. If you were to write down the numbers in this series, it turns out to be the same thing. So it's these numbers here. So 7 over 2 squared plus 8 over 2 to the third. And this is a really useful tool when you're doing problems in this section, because sometimes you might need a series to start at a particular index, but it's not at that index, so you can change it. Okay. All right. Okay, so since this is new, why don't we take a moment just to try these practice problems here. So here's 2 examples, and the direction says to perform an index shift, okay? So let me give you guys some time to try this on your own. How much time should I give you? I will give you guys 4 minutes. So hopefully you guys have pen and paper or tablet and pencil. This shouldn't take too long. Yeah, one person was taking stat. How many of you are taking stat this semester? Discrete math. That's not stat. Well, discrete math is a cool course though. Yeah, I never took that course, but I have like helped people with questions on that course. It's not like I know it's computer science, but it's a type of course where like you have to be so creative that like all the problems are really hard. It's hella discrete. Eight out of 20 for first exam. For stat last semester? Oh, for discrete math? Okay. How much is there to stat other than normal distribution and hypothesis tests? um, I mean, it depends. If you're talking about just stat 213, then that's pretty much it. But if you go further, there's more stuff. Like if you go further in stat, there's other distributions besides the normal distribution. I know they teach you uniform distribution in 213 as well, but I think that's about it. All right, let's go through these questions. So let's practice shifting indices. All right, number one. So we want to shift the index from 1 to 0. So let's go ahead and do that. Summation. How do you write this correctly? Like this. Okay. Summation as n starts from 0 to infinity. So we went from 1 to 0, which means we subtracted 1 from the starting index, which means we have to add 1 to everything in the formula, right? So it's going to be AR, replace this with an n plus 1 minus 1. Did everyone get that? Yeah, okay. And if you want, you can simplify this. So this is n equals 0 to infinity, a times r to the n power. Okay. All right, let's do B. So this one wants you to move the starting index from 1 to 3. So we're going to start at 3 now. And then to go from 1 to 3, you had to add 2, which means we have to subtract 2 from everything. So this would be n minus 2 squared over 1 minus 3 to the power of n minus 2 plus 1. Okay, so did everyone get that? Yep. Okay, good. So there's your exercise on shifting indices. If you're not convinced that these are correct, you can always just like write down the terms, but I mean, I'm convinced. So hopefully you guys are convinced. All right, let's continue. All right, so much like sequences and functions and everything, we have to figure out how to see whether these things converge or diverge. So how do we figure out whether a series converges or diverges? So we mentioned partial sums, right? Which was just the sum of the first however many terms. Here's the diagram again. So we have the partial sums S sub 1, S sub 2, S sub 3, S sub 4, and S sub n. So S sub 1 is just the first term. S sub 2 is adding the first 2 terms in a series, and then S sub 3 is adding the first 3 terms. So I want you guys to imagine S sub 1, S sub 2, S sub 3, S sub 4, all those partial sum numbers, and then put them together as a sequence, okay? So this thing right here on the right, this bracket S sub n. So that's a sequence where every number in the sequence is basically a partial sum. Now, if you were to find the limit of that sequence as n approaches infinity, that's basically going to tell you whether or not the series converges or diverges, okay? So in order to figure out whether a series converges or diverges, you just figure out the limit of the partial sums. Okay, so before we look at some problems, we have to go over one very useful test that we can use to figure out whether something converges or diverges. So what is this? This is a theorem. We're going to skip this slide. So the goal of this topic is to figure out whether a series converges or diverges. This particular theorem requires you to know whether it converges or diverges first. So we're going to skip this one. So ignore this slide. Let's go to the next one. Yes. So there's this thing called the divergence test, which will tell you whether or not a series will diverge. So let's read what it says. So it says, if the limit of a series, so A of n is a series, if the limit of a series as n approaches 0, let me say that again. If the limit of a series as n approaches infinity does not go to 0, then the series will diverge. And let's take a moment to convince ourselves why that's true. So let me go back to the board. All right, so here's the divergence test. So let's just think about this and use our intuition here. So let's say we have a series. Let me give you this one right here. So we have 1 plus 2 plus 3 plus 4 plus 5. And let's say it goes on forever all the way to infinity. So clearly the limit of this series as you go further and further does not go to 0. Is that okay? Is that obvious? So this particular series I gave you, this does not go to 0, right? Because our numbers are getting larger. So clearly it doesn't go to 0. Now, if I asked you the question of whether or not this particular series converges or diverges, what would you say? Diverges. Anyone say converge? So keep in mind that we're adding up all these numbers, right? We're doing 1 plus 2 plus 3 plus 4, and then we're keep adding and adding. So our sum, is that going to converge or diverge? What do you guys think? One student says diverge. Diverge. Okay, yeah, it looks like everyone agrees with diverge. So this is an illustration of like how intuitively we can think about this test. So if the numbers keep getting larger and larger, it's obviously going to go to infinity, so it's always going to diverge. So let's do like a counter example. Let's say I gave you a series such that the numbers get smaller. In other words, the limit does go to 0. So let's say I give you 110 plus 1 over 100 plus 1 over 1,000 plus 1 over I don't know. Yeah, let's just continue. 10,000. So this one, the limit does go to 0. Because the denominator gets smaller and smaller. But what about the actual sum? So this series has a sum. What do you guys think the sum will be? Will it be convergent or divergent? Convergent. Yeah, I would probably say convergent, right? Because it's getting so small to a point where it's probably not going to reach infinity. So this is probably convergent. I'm gonna write probably because we don't know for sure. But yeah, the main idea is that if your numbers don't go to 0, then it's never going to converge. So this is why the divergence test is true. And hopefully we'll see how it comes into play later. So let's go back to the PowerPoint. Yeah. Okay. So in other words, if the terms in a series do not approach 0, then the sum will be too large and the series will diverge. There is a note down here that says, do not misuse this test. So if the limit of the terms do go to 0, that does not guarantee convergence. Yeah, so that's a mistake that like a lot of students tend to make. They just assume that if a limit does go to 0, then that does that mean convergence? Because that's kind of like the opposite of the statement. And the answer is no, because there are examples where the limit does go to 0, but it can still converge or diverge. So, I listed a counterexample here. But as far as just doing a question goes, you can only state the series will diverge if the limit does not go to 0. And that's it. Like you can't modify that statement in any way. So hopefully that's okay. And then let's see if we can do an example regarding this. Yes, okay. So let's look at this one. This one says determine if the following series is convergent or divergent. So let's do it together. All right, so this series is summation as n equals 0 to infinity of 4n squared minus n cubed all over 10 plus 2n to the third. Okay. Let's list out a few terms of this series just so we can see how this looks like. So the first term is when n equals 0. That gives you 0, right? Because the numerator is 0. The next term is when n equals 1. So that's 4 minus 1. That's 3. And then 10 plus 2 is just 12. Okay. And then when n equals 2, we have 16. Yeah, I forgot to switch tabs. My bad. So right now I'm just listing the numbers in the series. So this one was n equals 0. This one is n equals 1. Now we're doing n equals 2. So this is 16 minus 8 over 10 plus, that's 8, that's 16. Okay, so the numbers in this series are 0 plus 1/4 plus 8 over 26 plus so on and so on. So that's how the series looks like. From this information, is it obvious as to whether or not this converges or diverges? Divergent? Maybe. Why do you say divergent? Does anyone else think convergent? Yeah, so the question is based off of the terms in the series. So I just listed out the first 3 terms, which is over here. So the first term is 0, and then the next term is 1/4, and then the next term is 8 over 26. So we're adding all those numbers together, right? A series is a sum of all the numbers. So if you were to imagine us adding all the numbers in a series, do you think it's convergent or divergent? Convergent. I mean, I could see how someone would say convergent because these are fractions, right? So maybe if you add them all together, you'll get a finite number. But I can also see how someone would say divergent because like we don't know if like what if the numbers get bigger or something, you know? It's going to be negative for larger numbers. Yeah, I think if you go further into the series, you might get some negative numbers. So yeah, I don't think it's not obvious, right? So I don't think we can really come up with an answer just by looking at it like this. So there's something we can do here, which is to use the divergent test. So why don't we do that? Because the divergence test will tell us whether or not it diverges. Yeah, obviously. So let's try it. So here's the divergence test. Um, let's see what happens if we take the limit of our series. So we want to do limit as n approaches infinity of 4n squared minus n cubed all over 10 plus 2n cubed. Okay, so what does this equal to? -1/2. Yeah, I think so. So yeah, you could just divide every term by the highest power, right? Or you can just say because the leading terms are both cubed, you can just take the coefficients. So this is -1/2. All right, so if the limit is -1/2, what can we conclude? Can we conclude anything? It diverges, not diverge. Wait, Devin, I'm waiting. You have nothing? Okay. Yeah, so let me see what the statement says. So it says if the limit is not equal to 0, then it diverges. So what is our limit here? Is it equal to 0 or no? It's not, right? So we can just say it diverges based on the divergence test. So because the limit is not equal to 0, we can say this diverges. Okay. Yeah. Are you guys all good with that? Yes. Okay. Yeah, it's kind of weird how this thing diverged because some of you or some of us thought it would converge, right? Because these numbers were quite small. But I guess like if you went further into the series, you would get some really big numbers. Like if you plugged in n equals, I don't know, like 1,000, that would probably give you like, I don't know, something close to -1/2. So if you're just adding a bunch of -1/2, that will probably diverge. But I have a question for you guys. So let's say we calculated the limit and we got a limit of 0. Can we conclude anything if we got a limit of 0? Based on the divergence test. No. Yeah, that's right. So the answer is no, because the divergence test just gives you a condition to test for something that will lead to divergence. If you get a limit that's not 0, you cannot say anything. So if you got a limit of 0, that can either mean converge or diverge. So that doesn't really help us. It's only when you get a limit that's not equal to 0 can you reach a conclusion. Okay, so just be careful on that. Truth table. What does limit equals 0 mean? Like when you take the limit of this thing right here. So if you took the limit of that, and if it happened to be 0, like that's what I meant. Yeah, so if you talk about like a truth table, I guess what you can say is that this is a statement, right? And then you could say the converse and the inverse are both not necessarily true, if you want to think about it like that. So that's the divergence test. Any questions? Okay, so moving on. Next thing we're going to talk about is a geometric series. So we looked at a geometric sequence before. Now we're going to look at geometric series. So it's pretty much the same thing, just with the summation sign because it's a sum now. So the regular way we write a geometric series is the first way over here. So it's a times r to the n minus 1, right? But that notation implies that you have a starting index of 1. So the first notation is summation as n equals 1 to infinity of a times r to the n minus 1. Some questions might write a geometric series differently. So they might perform an index shift. So instead of starting a geometric series at n equals 1, they might start it at n equals 0. And then if you do that, then the geometric series looks like this. So it's just a times r to the n, right? Instead of a to the r to the n minus 1. So both of these mean the same thing. They're both geometric series, and they're both equivalent. Anyways, so let's say you have a geometric series, so a sum of a bunch of numbers. Question is whether or not that series will converge or diverge. And the answer to that question is it depends. So over here we have this statement. An infinite geometric series will converge if the absolute value of r is less than 1. Who remembers what r represents in a geometric series or geometric sequence? Yeah, the common ratio, right? So the statement says a geometric series will converge if the common ratio is less than 1. Does that sound intuitively obvious to you guys? Why does a ratio need to be less than 1 for a geometric series to converge? If it's greater than 1, then it gets larger from the previous term. Yeah, that's true. So let's just consider two examples. So let's say I have this geometric series, so 1 plus 5 plus 25 plus 125 plus 625, and so on and so on. So that's a geometric series, right? Because we're multiplying by 5 to get to the next term. And then let's consider another geometric series. So let's do 1 plus 1/5 plus 1 over 25 plus 1 over 125, and so on and so on. So in this second geometric series, the common ratio is 1/5. But in the first one that I wrote, the common ratio was 5, right? So based off of these two examples, do you guys think you have an explanation as to why the common ratio needs to be less than 1 in order for a series to converge? So David, you made a good point. You're saying that if the common ratio is greater than 1, then the terms will always get bigger, right, than the previous term. What's the issue with that? So if the terms get bigger, well, if the terms get bigger, does it converge or diverge? Yeah, so it diverges because if you're just adding bigger and bigger numbers as you go on, then there's no way that your sum is going to be a finite number. So it has to be infinity and therefore diverge. So if you want a geometric series to have any chance of converging, then the common ratio has to be a number less than 1 because that makes it so each number gets smaller and smaller. Okay, so that's really the explanation as to why we need this condition here. So if the common ratio is less than 1, or more specifically, the absolute value of the common ratio, right? So if the absolute value of the common ratio is less than 1, then we can conclude that a geometric series will converge. All right, and then if it converges, then it has to have a finite number as a sum. So what is that number? So there's a formula here that that tells you the sum of a converging geometric series. So it's right here. I will label it in orange. It's a over 1 minus r. So a is the first term in the geometric series, and then r is the common ratio. And that is the formula for the sum of a infinite geometric series. Okay, we're not going to go through a proof of that. We're just going to have to accept that this is true, and we can use this formula. There is a proof on the internet, but we're going to skip that because I don't think any of you guys care. So there's the reasoning for why a geometric series would converge or diverge. All right, let's see if we can do some examples. Okay, so here we have 2 examples. These are actually going to be a little bit tough, but I don't think they'll be too bad. We'll do it together. So the directions say to determine whether the following geometric series are convergent or divergent. Now, I want you to look at these 2 examples right here. Actually, just look at part A. So part A has a series, and the directions are calling it a geometric series. Now, I don't know about you guys, but that doesn't look like a geometric series to me. Does that look like a geometric series to you? It doesn't. I don't think so. Do you think so? Because the geometric series is like a times r to the n minus 1 or to the n, right? So it doesn't seem to be in that form. So it doesn't look like a geometric series. So then why is the directions calling it a geometric series? It's a combination of two geometric series. Well, the index starts at 1. So let me just write the general form of a geometric series for when index starts at 1. So it's supposed to look like this. A to the a times r to the power of n minus 1. That's how it's supposed to look like, right? A is a constant, and then you have the common ratio to the power of n minus 1. So here, I don't know, it doesn't really look like that. But it actually turns out that if you were to do a little bit of algebra and some moving it around, you can probably like massage all the terms around to the point where it is a geometric series. So let's see if we can do that. Let's see, what can we do? Let me change colors. Well, I don't like how there's like two parts to it. So there's like this part and this part. So this is what I'm going to do. I'm going to make one of the exponents negative. So let me just make the first one a negative. So it's 9, and then it's to the negative times n minus 2. So the 4n plus 1. And then if I have a negative exponent, I can bring it to the other side of the fraction, but with a positive exponent. So this will be n equals 1 to infinity of 4 to the power of n plus 1 over 9 to the positive exponent, so n minus 2. Okay, did everyone follow that? Make sure you follow that because that was 2 important steps. And let me know if you got like confused as to any of that. Yeah, so looking at the 9 to the power of negative n plus 2. So the exponent is negative n plus 2. What I did with the exponent is I factored out the negative sign. So when you factor out the negative sign from the exponent, you're going to get an exponent of negative parentheses n minus 2. So now you can think of this as like a negative exponent. So I just brought it to the bottom as a positive exponent. Is that okay? All right. Okay, this is what I am thinking. So if we want to get it in this form right here, we need to have an exponent of n minus 1. So let's try to create an exponent of n minus 1. So right now, our exponent here is n plus 1 on top. Do you guys have an idea as to how we can make the exponent n minus 1? Index shift. I mean, you could, but I kind of don't want to. And the reason is because like the reason why we want an index of n minus 1 over here is because that's the form, or that's the exponent we want when the index starts at 1. So if you're going to shift the index, then we don't really need a exponent of n minus 1 anymore. So is there a way we can make the exponent n minus 1 without shifting the index? Factor out a 4. How so? Uh, 4 to the n minus 1 times 4 to the n plus 2. Oh, okay. 4 to the n plus 1 equals 4 to the n times 4. So what you're saying is I can write it like this. So 4 to the n plus 1 equals 4 to the n times 4 to the first power, like that? Okay. Well, yeah, you could do that, but that only gives us an exponent of n. But we want to get an exponent of n minus 1. So I think you can actually factor out something else to make it n minus 1. Factor out 4 to the 4 squared. Yeah, I think that's the better idea. So instead of factoring out in this term, like in this fashion, we can do it like this. So 4 to the n minus 1 times 4 squared. Yeah, I think that works. So remember that when you multiply two things with the same base, you add the exponents. So this is why we can do this. So we just created an exponent of n minus 1, so that's good. So let me continue our work now. Infinity to 1, 4 to the n minus 1 times 4 squared. Okay, let's try to do the same with the denominator. So our denominator is 9 to the power of n minus 2. How can we rewrite that so it's 9 to the n minus 1 times something? One over 9? Yeah, or you could just write 9 to the negative 1 power, right? That's the same thing. Yeah, so if you were to combine these two, you get 9 to the n minus 2 again, because you add the exponents. So let's write that. This is 9 to the power of n minus 1 times 9 to the negative 1 power. Okay, so that's fine. We got all the exponents to n minus 1 now. Notice how 4 squared and 9 to the negative 1 power, those are just constants, right? And then if you have constants, you can just bring those out of the summation. So let me bring it out. This is 4 squared 9 to negative 1. Summation of n equals 1 to infinity of 4 to the n minus 1 over 9 to the n minus 1. Okay, great. Whenever you are dividing two things with the same base, actually they don't have the same base. Whenever you have something in this form where you have the same exponents on the top and bottom, you can actually just write it as one term. So this is the same as 4 over 9, the whole thing to the n minus 1 power. Okay, so now this looks like a geometric series.
Doesn't that go to infinity at infinity?
Was that?
If you were to plug in infinity for n, wouldn't that just go to infinity? So that's divergent?
It depends. So remember what we say about um, geometric series. The common ratio has to be less than 1 in order for it to converge.
Mm.
Because if the common ratio is less than 1, then each term is smaller than the previous term, which allows it to converge. So this is a geometric series now. It is in the form, this right here is in the form a times r to the n minus 1. So what is the common ratio here? What is r?
4/9.
Yes. So here the common ratio is 4/9. And then is that less than 1?
Yes.
Yes. So based on that, we can conclude that this converges. And then because it converges, it has a finite sum. So the sum is equal to the formula that I gave you guys earlier, which was a over 1 minus r. So what is that? What is a here?
Is that what we had originally? That's the part that confuses me. A is what we had originally, right?
A is just a number in the that's in front of the common ratio. So this number here is just 1.
Oh.
Or you can think of it as like your first term in your series.
Okay.
A is your first term. Yeah. So in this case, a is 1. I mean, actually, it depends. If I didn't factor out this constant here, then this term would be a. But since I factored out, then a is just 1. So our sum is a over 1 minus 4/9. So this sum right here is actually the sum of this series here. But remember that our series is being multiplied by this constant. So we had to multiply this by 4 squared over 9 to the negative 1 power. So let me just figure out what this number is. All right, so this is 1 over 1 minus 4/9 is 5/9 times 16 times 9. So it's 9/5 times 16 times 9. Okay, yeah, this is a number, right? So this is the sum of the geometric series. So yeah, it's convergent, and it converges to 9/5 times 16 times 9. All right, so let me just recap this whole process. What we do is we just try to manipulate the original series to the form of a geometric series. And then based off of that, just observe what the R is, which will tell us whether or not it converges or diverges, okay? I guess the hard part is basically the rewriting it in that form. That's the part that usually takes the longest. But we have one more example to go through, which hopefully will make it a little bit clearer how to go about these questions. So this one right here. All right. So again, I don't know about you, but this doesn't look like a geometric series to me, at least not right away. But based off of the directions, we can conclude that it probably is. We just need to move terms around. So this one's index starts at 0. So that means we want to get it in the form n equals 0 to infinity of a times r to the n power. So this is the form we're looking for. Do you guys think you have an idea as to how we can start this? So remember that we're trying to get the exponent to be n. So let's see. -4 to the 3nth power. Is there any way we could rewrite the numerator so that we have an exponent of just n instead of 3 times n? Four to the third to the n. Yes, we can do that. So you can write it like so. -4 to the third power, all of that to the nth power. Wait, that's what you meant, right? Oh, wait, no, that was someone else. Okay. Actually, Yosef, what you wrote is isn't quite right. So what you have is -4 to the third times 4 to the n. This isn't quite the same because if you were to combine these, this is actually -4 to the 3 plus n, not 3 times n. Yeah, so just be careful on that. So when you multiply stuff, you add the exponents, but when you have a power to a power, that's when you multiply the exponents. So this one would be the way to rewrite it. But that's okay. So the numerator is fine. We have a power of n. More specifically, -4 to the third power is -64. So this is -64 to the nth power. How can we rewrite the numerator? I mean the denominator. So that one should be a little bit easier to see. We have 5 to the power of n minus 1. Five to the power of n plus 1. You said bring it to a number. No, so we just want to rewrite the denominator. 5 to the power of n minus 1 times 5 to the first power. Let me see. 5 to the n minus 1 times 5 to the 1. I don't think this is how you would rewrite it, because this is what we have originally. So I don't think this is the same. Devin, what did you propose? 5 to the n times 5 to the -1. Yeah, I think that's the same. Yeah. So this is equal to 5 to the n minus 1 because you add the exponents. Yeah. So that one's good. All right, let me rewrite that. 5 to the n times 5 to the -1. Okay, great. So all the stuff has a power of n now, which is what we want. Shouldn't we do an index shift before this? We don't want to do an index shift because this power of n, we only want this to be the power because the index starts at 0. So if you were to shift the index to say like n equals 1, then you need to use the other form, which is a to the r to the n minus 1. So there's really like no point in shifting the index. we just want to try to match the exponent to the index, like, you know, based on which form we want it to be in. So yeah. Anyways, let's continue our work here. 5 to the -1 power, that's just 5 in the numerator, right? So let me write it in the front. I'll just keep it inside the summation. So this is 5. And then we have -64 to the nth power. On the bottom, we have 5 to the nth power. And then, like before, when we have these two things to the nth power, we can combine it into 1. So this is n equals 0 to infinity of 5 times -64 over 5 to the nth power. Okay, so I think we have gotten it in the form, right? This is in the form of a geometric series. Can you guys see your A and your R, your first term and your common ratio? So we need to identify those two things right there. Yeah, so what is our common ratio here? It's this thing, right? This is our common ratio. So R is -64 over 5. So based off of that common ratio, what can we say about our series? Yeah, so because our common ratio is too large, well, technically it's small, but the absolute value of the common ratio is not less than 1. So does it oscillate? I don't even know, but it doesn't matter. So the absolute value of R is not, how do you write not less than? I don't even know. Not less than 1. This diverges. Okay, so that means that the sum of, or this series has a sum that's either infinity, negative infinity, or does not exist. Okay. All right, so those are the examples that we have been provided with. These are kind of the harder examples, so don't worry too much, but hopefully you guys get the main idea. So you want to convert it into a form of a geometric series and then just observe what R is and then go from there. All right, any questions so far? What exactly is the definition for the R thing? R is called the common ratio. So it's the number you have to multiply to get from one term to the next. Like, oh, the behavior. Yeah, so R is like, it determines whether your sequence gets smaller or larger as you go on. So like, if I just gave you like the number, I don't know, 2, and I told you to like keep multiplying 2 by itself, this will give you 2 and then 4 and then 8 and then 16 and so on, right? But if I gave you a number like 0.5 and I told you to keep multiplying it by itself, this doesn't get larger, this actually gets smaller. So this gives you 0.5, 0.25, 0.125, and smaller, right? So the main idea is that when you have a common ratio that's less than 1, your terms start to get smaller instead of bigger, which is why it converges. Would r equals 1 also converge? I don't think so. Yeah, let me see the definition again. Let me go back to the PowerPoint. Yeah, so the PowerPoint says that r strictly has to be less than 1. The reason why r cannot be 1 is because if r was 1, then the formula for the sum will become, the formula for the sum of a series will become, what's that term we divide by 0 called again? Oh yeah, undefined. So yeah, that's why r cannot be 1 as well. So if r is 1, that's also divergent because then the sum is undefined. So r strictly has to be less than 1. Okay, so hopefully I answered your question about like the behavior for R. Yeah. Okay, so let me see what I have next. Okay, we have a couple more things to say. So let me just go back. All right, so I have some practice for you guys. These are actually questions that I took from your homework. So why don't you guys try these since you're gonna have to do it eventually anyways. So it's the same as what we've done, geometric series, determine whether it's convergent or divergent. These are easier. So I'm gonna give you guys 5 minutes to try these and then we'll go through it together. Oops. All right. So remember to get it in the form of a geometric series, and then you should have the answer. How are you guys doing? Transfer apps got you pretty occupied. Where are you transferring to? Yeah, I meant with these example problems, but that's okay. We can talk about whatever. Okay. What is it that you want to study at those places? I see. Okay. I mean, they have that at Hunter too, don't they? So I heard Hunter's computer science department is terrible, though. All right. Do you guys need extra time or no? All right. Well, it doesn't matter. We're going over the questions anyway. So let's do this. Switch tab. All right. So can someone tell me how to write the first series in summation notation? So this is this summation of do you want to start the index at 0 or 1? Did you guys have time to finish it, or I don't know. I thought 5 minutes should have been enough. All right, so we want it in one of the following forms. We want it either like this, AR to the N, or you want it like this, AR to the N minus 1. I mean, they're both the same thing, so it doesn't matter. One? Okay, let's start at 1. N equals 1 to infinity. So that means we need A, and then we need R, and it's to the power of N minus 1. So A is our first term in our series, which is just 10. And then what is the common ratio here? Negative 1/5. Yes. So R is negative 1/5. All right, so that's your geometric series. Based off of this form, can we say our sequences or our series is convergent or divergent? Yes, this is convergent because our R is less than 1. And then if you wanted to, you could say what the sum is because convergent series has a sum. The sum is A over 1 minus R. Okay. Yeah, thank you. Whatever that is. So that's your sum. All right, let's do number 2. So this one, we had to get it in the form of a geometric series. Because the index starts at 1, we need to have the exponent be n minus 1, right? So the numerator is fine. It's the denominator we need to change. So let's see how we can do this. N equals 1, infinity. -8, and minus 1. So how can we get the denominator to have a exponent of n minus 1? N minus 1 times, yes. So we can rewrite it as 9 to the n minus 1 times 9 to the first power. Yes. So therefore, just move this. We can write it as 1 over 9, right? I just bring the 9 to first power in the front. And then this is -8 over 9 to the power of n minus 1. Let me know if you want me to write the middle steps. I just skip like a couple steps in the algebra. But based off of this form, is it convergent or divergent? Yes, this is convergent. Right? And then if I ask you what the sum is, you would say it's A, which is 1 over 9, over 1 minus the common ratio. Okay. All right, last one here. So our index is 1 again, which means we want to have n minus 1 as our exponents. So the denominator is fine. We need to rewrite the numerator. Can you just index shift, find a number, so the first few n values, then create a geometric series formula? Probably, yeah. There's multiple ways of doing these problems. As long as what you do is mathematically correct, should be fine. But yeah, if there's a way to index shift these and then get it in the right form after that, then yeah, by all means. So this one, I can keep the denominator. And then the numerator, I can write it as 6 to the n minus 1 times 6. Yes, okay. So this is equal to summation of 6, and then 6 over -4 to the n minus 1. All right, so this one, convergent or divergent? Yeah, so this one is divergent. All right, so hopefully this clears up the process of doing these problems a little bit more. Let me go back to the PowerPoint. All right, so we have the only things left in the PowerPoint is basically two special cases, which aren't really too important. So I'll just save those for next time. This will probably take like another 10 minutes of talking, but I'm just gonna call it here for today. So next time we're going to just finish this section 8.2, and then we'll start the next chapter, which is 8.3. You can start your homework now. So you do have enough knowledge to finish all of homework 8.2. So let's stop here for today. Have a good weekend, everyone. And I'll see you on Tuesday.
Wait, James, when do we have our next test?
I estimated November 12th.
Sounds good.
That's if everything like goes according to schedule. So we still have like 1.5 more lectures. So if it's not November 12th, then it'll be the next lecture after that, depending on how fast we go. If we need another day to talk about stuff. Yeah.
Gotcha. Thank you. Bye.
Yep.